Greeting. Welcome to the lecture of Introduction to Power Engineering. In today's lecture, we will discuss about the distribution power generation resilience characteristics and what control strategy transmission system demand from distribution power sources. Further, we will look the grid codes that distribution generation system needs to fulfill. Renewable energy sources are variable, uncertain, and non-dispatchable. Consequently, the distribution power generation system based on wind and PV resources may create severe issues, especially in response to extreme weather and in variable working conditions. This property is referred to as the resilience of the distribution power generation system. The resilience of the distribution power generation system characterizes the capacity to tolerate disruption and the ability to recover from event. To enhance the grid resilience, there are three major steps: distribution grid planning, enhanced operation, and emergency management. Many controls demand at the converter level and or system level are related to the resilience of the distribution grid during the operation or in contingent situation. In this flow diagram, the operating time sequences for distribution power generation system are shown in connection with the resilience of the distribution grid implemented at different levels. In normal operating mode, the distribution power system should be controlled at the converter level, while it should also be coordinated among the entire distribution system. In the case of unexpected temporary grid incident, the grid voltage level may decrease significantly. During this period, the distributed generator should remain connected in a short period, being the fault right through operation. They must support the fault right through operation. Beyond this short period, the protection devices scheme should operate, and it has to be operating and activate the anti-isolating operation. When the grid is completely out of service with the application of protection devices, the distribution generator may still power the critical loads. Alternatively, together with the backup energy, they can help to restore the distribution grid. In this case, a coordination between the transmission system level or the storage system and the distribution system may be necessary. Once the fault is removed from the transmission system or within the network, the remaining the distribution grid can be resynchronized with the network and start working normally. For the distribution power generation system, the grid requirements under normal operation includes its tolerance to frequency and voltage deviation. That is, how much the frequency and voltage can vary without requiring action from the distribution power generation system. Accordingly, how the corresponding active power control and reactive power control are performed. In general, the frequency and voltage deviation windows can be divided into the following three zones: continuous operational zone, constrained operational zone, immediate disconnection zone. Grid codes define different duration of distribution power generation system at which they must operate normally depending on the network frequency variation. A typical frequency and voltage tolerance for wind distribution power system is shown in this diagram. When the frequency and voltage of the distributed grid are within the 59 to 51 Hz and the voltages are zero point 0.9 to 1.1 per unit respectively, the wind distribution power generation system should remain connected in the normal operation mode with 100% power injection. When the grid frequency is in the range of 47.5 to 49 Hz or 51 to 51.5 Hz, then the generation system can remain connected to the network and produce normally up to 30 minutes. Beyond this time, either production needs to be reduced or disconnect it completely. Similarly, when the grid frequency fall in the range of 47 to 47.5 Hz or 51.5 to 52 Hz, then it can operate normally up to 30 seconds but disconnect it afterward. Once the grid frequency rise above 52 Hz or drop 47 Hz, then the distribution generation system must be disconnected from the network immediately. So the capacity of PV distribution power generation system is low compared to wind distribution power generation system, but expecting that the PV system installation would be drastically increased, the DSO imposes basic requirement to guarantee the quality of generated power and ensure a stable connection while considering the PV system. In IEEE standard 929-2000, the boundaries of the grid voltage and frequency are specified for PV. The grid code says that in normal operation, the PV distribution generation system should maximize the output power, which is known as maximum power point tracking control, as well as the converter system that are interfacing the PV system with the grid must have total harmonic distortion level lower than 5%. When a PV distribution power generation system is installed with the higher power capacity to medium voltage to high voltage distribution network, then the power injection from the PV distribution generation system can significantly affect the frequency and voltage profile of the distributed grid. The operational characteristics of PV distribution power generation system with respect to frequency and voltage deviation is illustrated in this diagram. This example is for 50 Hz system in which PV generation system should continue working as normal operation within the frequency range between 59.3 to 60.5 Hz, and the PCC bus voltage should be between 0.88 to 1.1 per unit. The PV system should disconnect within the 6th cycle if network frequency drops below 59.3 Hz or rise above 60.5 Hz, such as shown over here. Further, if PCC bus voltage fall in the range of 1.1 to 1.37 per unit or 0.88 to 0.5 per unit, then PV system must be disconnected from the network within 120 cycles, such as this region. And if the voltage drop below 0.5 per unit, then it must be disconnected within 6 cycles. And if the voltage rise above 1.37 per unit, then it must be disconnected within 2 cycles. Furthermore, owing to various events such as lightning strike and short circuit, the distributed grid may enter a faulty condition. In this case, the distributed grid voltage can be increased or decreased, that is, voltage swell or sag can happen. As more renewables has been connected to the distributed grid, the grid code requires the distribution power generation system to ride through fault, low and high voltage faults for the stability concern of the entire distribution network. In this diagram, a low voltage ride-through requirement is demonstrated for wind, which is represented by the solid line, and PV, which is shown with the dashed line. The diagram also illustrates grid codes for two different countries, that is, the blue color represents the Spanish grid code and the red color represents the Danish grid. Generally, the low voltage ride-through requirements can be divided into three zones, such as Zone A, Zone B, and Zone C. In Zone A, the distribution power generation system should remain connected to the distribution grid and maintain the power production. When the distribution grid voltage level is in Zone B, the wind distribution power generation system must also stay connected to the grid. Simultaneously, the distribution power generation system must provide maximum voltage support by injecting the reactive current. The reactive current support is for stabilizing the entire faulty distribution grid. In contrast, the wind DPGS is allowed to disconnect only when the grid voltage level sag into zone C or, or the fault duration exceeds the limit. So in zone C, the distribution power generation system must be disconnected. Similarly, in the case of high voltage ride-through, in some countries, the distribution power generation system should also remain connected and be able to provide reactive current support upon demand. Nevertheless, when the grid fault is cleared, the production of distribution power generation system should be resumed at limited rate. As previously mentioned, reactive current from the distribution power generation system are required in the case of distributed grid fault. Here, the grid code requirement of injecting reactive current by the distribution power generation system is illustrated. It says that when the voltage level exceeds the range of 0.9 to 1.1 per unit, the reactive current supply is prioritized to support the grid voltage recovery. During this period, the active power production should be maintained if possible, but this is not required because it may trigger the inverter protection. According to Spanish grid codes, as illustrated with the blue line over here, if the voltage drops 0.85 per unit, such as these point, then the distribution power generation system must inject reactive current up to 60% of its nominal current. In this case, the injection of active current is reduced. The amount of reactive current should be increased up to 80% if the grid voltage or at PCC bus voltage drops to 0.5 per unit. If the grid voltage drops further, then the 100% reactive current must be injected by the distribution power generation system, such as here. Similarly, the red curve represents the Danish curve grid codes, which states that the 100% reactive current must be injected. Here, the injection means the capacitive reactive current, in case if the grid voltage reaches 0.5 per unit. Often, the grid codes provide the guideline when the grid voltage rises, such as these regions. According to Spanish grid code, the distribution power generation system must inject inductive current when the grid voltage rises above 1.1 per unit. DPGS should also stay connected within the certain defined period when extreme recurring fault occur. Overall, the fault ride-through operation is a scheme for tolerating voltage dip and rise in the distributed grid and thus preventing the collapse of the entire system. The control of power electronics converters of DPGS can provide fault ride-through capability. Either the grid frequency or the voltage level may be of outside the boundaries due to variability and uncertainty of renewable sources. In the case of frequency deviation, the DPGA should be able to automatically change the active power production and must also perform frequency control. These are known as frequency response and frequency regulation, which is achieved through the frequency active power throughput relationship. Then, the Danish grid core requirement of active power reduction by the distribution power generation system with respect of network frequency is illustrated over here. Here, frequency response and frequency regulation profile is shown, where P available is the present available power, P min, such as over here, is the minimum power, P delta is the power difference, F set is the frequency set by the TSO, and F minimum and F maximum are the minimum and maximum distributed grid frequency respectively, such as shown over here, this frequency and that frequency. The generation unit should be able to reduce the active power production in the range of 2% to 12% of the nominal power, according to any critical frequency point. Here, P minimum can reach to 0.0 per unit. The droop curve should be implemented when the frequency is measured. An accurate frequency measurement is necessary to ensure stable operation and fast dynamics. To further elevate the impact of the fluctuating power generated by the distribution power generation system, different active power control constraints have been introduced in recent grid cores. It is necessary to keep the active power constant during wind speed change or solar radiation changes, or limit the ramp rate of the active power. Different constraint function required for the wind and PV distribution power generation system, such as the absolute production constraint, the delta production constraint, and the power gradient constraints. These active power control features or functions are defined in order to prevent the instability or overloading of the distributed grid. An absolute production constraint is used to avoid overloading, and active power output of wind farm is constrained to a predefined megawatt. A delta production constraint is used to control frequency and active power output of wind farm and is constrained in proportion to the possible active power. A power gradient constraint is used to limit a rapid increase of active power output, and active power output can increase with the maximum speed. All these active power constraints can be realized through the control of power kernels. Another grid stability index is the voltage level. By controlling the reactive power, the voltage level is regulated, which is known as automatic voltage regulation. The reactive power exchange between the distributed generator and the distributed grid can change the voltage profile at the point of common coupling. Here, abbreviation of PCC means point of common coupling. The grid course of voltage regulation is illustrated in this diagram. In general, the reactive power requirement is usually expressed in three different ways. The Q control. In this control function, the reactive power should be controlled independently of the active power at the PCC. Power factor control. The reactive power is controlled proportionally to the active power at the point of connection, which results in constant power factor. And voltage control. This function controls the voltage at the voltage reference point by changing the reactive power injection. The reactive power control and voltage control function are mutually exclusive, which means that only one of the three aforementioned functions can be activated at a time. So this diagram illustrates the curve through which depend the reactive power feed into the system and the voltage rise and drop. Unintentional islanding can be one of the main technical issues for wind and PV distribution power generation system. Islanding operations occur when the power supply from main distribution grid is interrupted, but the distribution power generation system continues to supply power to the network or the local load. Islanding operation result in the tripping the line or damage to connected equipment due to the out of phase closure, and safety hazard for distributed system personnel that assume de-energizing line during the island. Islanding occur more easily in highly penetrated distribution generation system network. To avoid these serious consequences, safety measures called AI requirements have been issued and embedded in the wind and PV distribution power generation system. The main approaches for islanding detection includes the following. Grid resident detection, which requires either an advanced communication system or an external switched capacitor at the PCC, which increases the entire system complexity and cost. External switched capacitor detection method, which is based on the concept that an external capacitor being periodically switched on in parallel with the grid produces a zero crossing delay proportion with the grid impedance. Another approach, which is called inverter resident detection, in which the relay exclusively on software implementation inside the distribution generation system control system, which does not require any hardware modification. In another approach, the inverter resident detection approach has gained popularity. Commonly, it can be categorized into three groups: passive detection, active detection, and hybrid solution, which is the combination of passive and active detection. The reliability of the islanding detection method can be represented by the non-detection zone, which is called NDZ, defined in the power mismatch space where the islanding is not detectable and there is potential for parasitic drips. Example of passive detection method is illustrated over here. Here, UF and OF stand for under and over frequency, and UV and OV stand for under and over voltages. In passive detection method, voltage and frequency monitoring of the distribution grid is typically performed in order to trip the inverter in case of under voltage and over voltage and under frequency and over frequency protection. The worst case of islanding detection is represented by the condition where the active power and reactive power are balanced, in which there is no change in the amplitude or frequency. The passive method has several advantages, such as a low cost and a simple and straightforward structure, as only the mentioned voltage and frequency are used. This results in a large NDZ area which can be precisely determined in practice. However, in most cases, passive islanding detection is considered insufficient for AI protection in the distribution power generation system. Active islanding detection methods are based on the generation of small perturbation at the output of distribution power generation system inverters. Small changes in one of the power system parameters, such as frequency, phase, and harmonics, can be identified. If islanding occurs, these small changes are amplified. Hence, compared with the passive method, the active islanding method can quickly detect islanding with a smaller NDZ area. The most common used techniques are frequency drift, voltage drift, and grid impedance estimation. However, even small perturbation can push the distributed grid voltage and frequency out of nominal range. In this case, in the case of weak network, the small changes can cause the instability of the entire distributed grid. Hence, further efforts should be directed toward designing proper active AI method for large distribution power generation system. Hybrid islanding detection method uses the strength of the passive and active methods. Here, the hybrid islanding detection overcomes the limitation of the active and passive techniques and exploits the advantages of these techniques. In most cases, passive detection is used to detect islanding first. If no clear disturbance is detected, perturbation are injected, that is, active method are enabled. However, this may lead to the larger NDZ. When the distributed grid is down, the distributed generators such as wind turbine or PV panels may be required to power critical loads. Further requirements includes that the islanding and grid connected operations should be seamlessly switched. Also, the detection of the distributed grid failures and resynchronization are essential to the operational transition. In short, distribution generation systems should be able to operate in the islanding mode. The employment of the distributed generators improves the grid resilience, as critical loads can still be powered on when the distributed grid is under disruption. In this lecture, we have discussed about the grid core requirement of distribution power generation system and review what control scheme and operational behavior power generation unit must have to fulfill the grid codes. Today's lectures end here. Thank you for listening.